Tough ones.
Okay, hello everybody, and welcome to the latest Hubble Hangout. Today, my name is Tony Darnell. I'm the social media manager at the Space Telescope Science Institute, and today we're going to be talking about very, very far away things, notably the most distant galaxies we've ever seen. And with me today, I've got lots of really I'm assuming highly qualified people to be able to talk about this. No, I'm just kidding. We have a lot of experts, and so we talk about some new discoveries on some of the most distant galaxies we've seen so far. With me, but before I get started, let me just say we are ready to take your questions and comments. Casey just joined us. Via Twitter with the hashtag Hubble Hangouts. If you can comment on our event page as well as on the YouTube channel. I'm looking at comments on there as well as you can ask us directly here in the Google Plus event page. Already we're starting to get some questions now, so that's great. So with me today is Dr. Stephen Finkelstein from the University of Texas at Austin. Hi, Steve. How you doing?
Good. Hi, Tony.
Good, thank you. And with me is also Renska Smit from Leiden University. Hi, Renska.
Hey, how are you?
Hi, I'm good, thank you. Also, back from the Frontier Fields Hangout, we might remember Mark Dickinson from the NOAO. Hi, Mark.
Hi there.
And a good friend of mine, Dan Coe, at the also he's a you are a postdoc, right? At Space Telescope Science.
I'm on the staff now, actually.
Oh, are you? Congratulations. Okay, and he's the
you can buy us a drink next time.
That's right. That's right. Congratulations, Dan. He's with also with Space Telescope Science Institute, and he knows a thing or two about most distant galaxies as well, because you may remember, if you've been following these Hubble Hangouts for any length of time, he had one or two things to say about faraway galaxies, and we're going to talk to him a little bit more as well. Also, who just joined us, Casey, and I'm going to have you pronounce your last name for me.
Sure, Casey Papovich.
Casey Papovich, and you don't have your lower third up. You just joined us, so can you tell us where you're from also?
Sure, I'm at Texas A&M here in College Station, Texas.
Oh, welcome. Okay, great. And I didn't get a chance to brief you on what to expect. You're going in cold turkey. We're live right now, so if you have any questions or if you have any problems with anything, let me know, and we'll all sort of step you through it. So, anyway, welcome everybody. You may notice that we don't have Alberto here today. He has not joined us because he is still getting set up in his new job over at Northrop Grumman, so he will hopefully be joining us in the next hangout that we're going to be having after Thanksgiving. And Scott Lewis also couldn't make it. So it's me here moderating the whole thing. I hope I'll ask for your patience if it takes me a while to get certain things up on the screen share. So let's get started. The reason we're having this hangout is there was an announcement a while back about a new, and let me just read the press release headline, because to me it was a little bit, you see these all the time. Astronomer, with international team, identifies earliest galaxy ever detected. And we seem to be seeing a lot of these kinds of headlines. And so, Stephen, you were the lead author on a paper, I believe, I believe it was in Nature, correct?
Yeah, that's right.
Okay, you want to tell us a little bit about it?
Sure. So, well, I think we'll talk a lot during this telecon about how we find these distant galaxies.
Yes.
But I'll skim over it for right now. So we use the Hubble Space Telescope, and we take lots of really great, really long duration images of the universe to try and find really distant galaxies. And you can do this in a variety of ways, but we basically rely on the colors of the galaxies to figure out which ones we think are far away. And broadly speaking, we look for the really red things. We know that because the universe is expanding, things that are really far away from us are moving really fast away from us. And due to the Doppler effect, or the stretching of light waves from really quickly moving objects, they tend to look really red. And so we can get a pretty good estimate of which ones are far away by essentially looking for the red things. But to be certain about their distance, we need to follow it up with spectroscopy from the ground and try and measure a very precise distance to those galaxies, not only to get a precise distance instead of just an estimate, but also to make sure we're not kind of folding in some lower redshift or more close to home galaxies that can masquerade as these distant galaxies. For example, there are low redshift galaxies that are just red because they're old or have lots of dust, and so we need to make sure they're not in our sample.
So you're looking at various areas with the Hubble, and then you see them in red filters, or you see them with certain optical properties, and then you want to go back and look at them again with ground-based telescopes or some other telescope to confirm that they are in fact not just inherently red.
Yeah.
So the Nature headline reads, "A galaxy rapidly forming star 700 million years ago after the Big Bang at redshift 7.51." So, is this the most distant galaxy we've seen so far?
That's the question of the hour, I think. So when we find galaxies with images, we frequently refer to them as candidates for galaxies because we are not absolutely sure of their distance until we follow them up and detect them with spectroscopy. It's extremely difficult because they're really far away, so most of these most distant galaxies we hear about remain candidates for now. Most of them, and as Dan will tell us a little bit, we think are probably real, but we don't know. And so we refer to this one as the most distant spectroscopically confirmed galaxy that we know of. And so the many of the other ones may be likely real, including Dan's that he's published as well. But we don't know until we get a spectrum.
So this one's confirmed then. It really
Yeah.
is a 7.51.
That's right.
All right, well, Dan, a while back, you and I had a little hangout, I recall, and you were telling us of a galaxy how far away? What was the redshift on that?
So it's redshift 11.
Okay.
And so that's 420 million years after the Big Bang. And I guess Steve's is, what's the number on yours, Steve?
7.51.
Yeah,
Right.
700 million years after the Big Bang.
Right.
Measly 280 million year difference.
Right.
Right.
Not the rub it in. But as Steve said, I mean, this spectroscopic redshift really is the gold standard for these distant measurements, and it's a confirmation of how far away it is. And we're also pretty confident in ours being at its distance, but we actually have observations coming up on the Hubble telescope to try to get a spectrum of this galaxy and to try to confirm this the distance for that one too.
Okay, so the Z11 galaxy that you were talking about earlier was found as part of a survey, the CLASH survey, if I recall, and
Right.
using gravitational lensing. And but you're saying that that while you're confident of the number, it has not been spectroscopically confirmed yet, correct?
That's right.
Okay, and Stephen, yours has. So right now, the important thing is it's kind of like Kepler with exoplanets. Kepler comes up with a lot of candidate exoplanets, but they're not. It's not until someone else goes behind and actually confirms that they're there through some other means, whether more light curves or more accurate measurements, can we be sure that those things are really there. So that's pretty important. So Renska, can you tell us a little bit about what was your role here? What were you a part of this team?
No, I was. I'm part of the CLASH team, but I wasn't part of either of those candidates.
So are these things then that you're studying as part of your PhD work?
I am studying a couple of galaxies at redshift 7, but they're not quite the highest redshift galaxy. We're not trying to find the highest. We're not trying to go for that record. What I think is really interesting about Stephen's object is the fact that it also in the Spitzer colors there's very peculiar colors, which might be due to oxygen. And well, we don't know what it means yet, but I'm also looking at objects that have very interesting Spitzer colors and might be oxygen rich or ionized oxygen rich. Yeah.
Okay, great. And so what is it, when you say you're not looking for the most distant, what are some of the redshifts that you're currently looking at with the data that you're seeing? What are some of the typical redshifts?
They're just maybe 100 million years. So it's just under 6.8.
And are you
100 million years.
Yeah, really? Okay, and Mark, so what can you tell us about these high redshift galaxies? What are some of their characteristics?
Well, we've been pushing out this frontier of distance and redshift, bit by bit over the years, and sometimes it all seems very incremental. It seems like, we've gone from 6.8 to 6.9 to 7.0, what's the big difference? But actually, if you really look back with a little bit of a time baseline, 10 years ago, galaxies at redshifts 3 and 4 were a pretty big deal, and now we've pushed back, billions of years earlier in cosmic history, and much closer to the very earliest formation epoch of galaxies. And we're seeing the galaxies changing. We really are. The galaxies at redshift 6 seem different than the galaxies at redshift 4, which are different than the galaxies at redshift 2. We're really seeing galaxy evolution that we can measure. And that's been one of the big changes of this, very high redshift game over the last few years. Not just that we pushed that redshift frontier farther out and farther back in time, but that we're seeing the properties of these galaxies changing. We're seeing them getting brighter with time as the universe ages. There's more of them, and especially they seem to be brighter with as time goes on, as they form more stars. It turns out they keep forming stars faster and faster, and so they get brighter. We're seeing them building up their masses. The stars that they form keep accumulating, and so the galaxies get more massive with time. We're seeing them getting dustier. Star formation, when galaxies form young stars, they also produce dust during that time, and that dust is polluting the gas within those galaxies and is affecting the light that we see from them. We're seeing a variety of changes, even changes in the kind of spectral signatures like the oxygen lines that Renske was talking about. We see differences in the strengths of hydrogen lines and metal lines of these galaxies at early times versus later times. So we're getting all these clues as to that earliest build-up process of galaxies. This is the era in which galaxies were really building up for the first time. At the kind of redshift 7 era that we're looking now, only, say, 1% of the stars in today's universe had formed. The galaxies that we're finding at redshift 7 make up only 1% of today's stellar mass density in the universe. By the time we get to a redshift of 2 or 1, we're up to 50% of that mass. So it's a period in which galaxies really grew rapidly, and we're watching that happen.
So I have the image up here that Steve sent me of the press release. Steve or maybe Casey, would you like to comment on this a little bit? Can you guys see it okay?
Yeah.
Yeah, we can.
Go for it, Casey. It was one of our colleagues at Texas A&M that made this, so you go.
Yeah, right. This was actually made by a postdoctoral researcher working with me, Vital Tilby, who was part of the group that went with Steve out to Mauna Kea. Well, I guess you guys observed from Waimea down at the base camp of Keck. But they were using the Keck telescope, and so he made this image. It's a composite. The background is a very deep image. It's the one taken from the Hubble Space Telescope. It's a false color image, so it's data taken in the infrared using the new wide field infrared camera that they installed in 2009. They installed that on the Hubble, and that really allowed all this imaging to take place. The zoom in shows the image of this galaxy. Again, the light, you're seeing the rest frame ultraviolet light, but it's been shifted with the expansion of the universe out into the infrared, and so that's the morphology. That is what the galaxy looks like to us. And of course, we're seeing the light from this galaxy as it came 13.1 billion years ago.
So this is very typical of a lot of things. Someone just snapped a picture. So this is very typical of a lot of the early galaxies that we see. It basically is it's very blobby. It's kind of featureless, and to kind of go along with what Mark was saying, that we can see the sort of evolution of these galaxies as we go forward in time. So here we're looking at things just a few hundred million years after the Big Bang, very early in the universe's history, and really it just looks like a red blob to me.
Looks like two red blobs, actually. Mm-hmm. Kind of nice.
That's true. There is kind of a little bit of a external blob there to the lower right. So these are pretty typical of these galaxies, right? I mean, these early galaxies, they didn't look like much, were they?
No, that's right. So there's a lot of evidence that these things were probably highly gas-rich. So they had a lot more of hydrogen gas and other gas, the fuel they're going to use to form stars, and so instead of, as Mark was pointing out, instead of having a lot of stars, these galaxies have a lot of gas. And so when they do start forming stars, they look very disheveled and very immature. And it's only later, after they start forming their lots and lots of stars, and the galaxies grow to have the more mature shapes you see. And in fact, in the backdrop of your image, you'll see many galaxies that are closer to us. There's one right above the box.
That's right. Right, this one right here. Yeah, it looks a lot like the Andromeda Galaxy.
Right. That's a good analogy. So I mean,
Yeah.
in this one image, you see many billions of years of evolution in cosmic history, and the galaxies in the foreground are these very mature galaxies that have formed lots of their stars, and the ones that we're just seeing for the first time with Hubble are just forming very small amounts of stars compared to what they'll eventually grow into.
Well, I mean, this is, this is really amazing to see the two just so close together. So, but I guess it makes sense, doesn't it, guys, that these galaxies would be rich in gas? I mean, after all, the universe was back during this time mostly just a big sea of gas, right? I mean, and it's finally starting to clump up into these little clumps that are, I guess, sort of lumpy galaxies, right? Doesn't that make so? So I guess my question is we are looking with these not too long after a period in the universe's history when there were no galaxies, right? It was just gas everywhere.
Yeah, and I think that's right, and that's really what we're looking for. We all justify what we do in different ways, but I like to think we're looking for the first galaxies to form in the universe, and we do it in the simplest way possible. We just look further back and further back and further back until at some point we won't see anything anymore. And so far with Hubble, we've essentially gone back as far as we can, be it redshift 8 or redshift 11. They're kind of all pretty close together, and we continue to see galaxies, and we've kind of hit the limit of Hubble.
So what is that point, do you think? What Z number is it where we won't see any more galaxies?
15.2.
Does that question even make sense?
No, it does. It's a little bit ambiguous. So we know that with the James Webb Space Telescope, we'll be able to go to yet higher redshift because it will have redder wavelength coverage. The aperture will be much larger. The mirror is much larger, so we can see much fainter galaxies. So if with the Webb we still can't see anything, then the Webb won't be able to see the tiniest, the very smallest galaxies that are forming, which really are probably the first galaxies. But we will be able to say, okay, when did the first galaxies form that have at least a mass of 1 million suns, which is actually a pretty puny galaxy? And we will be able to answer that. And I think current theories say it's anywhere from maybe redshift 10 to redshift 20, broadly speaking. And that's the regime we'll really be able to cover with the Webb and pin it down pretty well, I think.
Okay, who wants to try this one? This question is, it's about the Z number. We've been talking about it a lot, and I know that we've talked about what it means to other people before, but who can give me a shot? What does the number Z mean? Is this a good question for Renke? Renske, I'm sorry.
What does
that Z number mean? What does it represent?
It has to do with the expansion of the universe. So the beginning of the universe is practically at Z infinity. So it's just a number that indicates how close we get to the beginning.
So so it's just a number, right? It's a dimensionless number that just has some kind of relevance as far as how far we're looking back and what period of the universe's history we happen to be looking at. Is it correlated, guys, and this is to anybody, is it correlated to an exact distance?
Yes. So I'll jump and take this. So it's actually, you can take it one step further, which is the redshift is also telling us exactly how big the universe is as we look back in time. Of course, as we look back in time, you don't see galaxies as they look now. You see them as they looked when the light left from them. And they exist at we call it a redshift because that's actually what we measure. As Renske was saying, or as Steve was talking about, you measure an emission line, and that tells you what the redshift is. It's the scale factor of the universe. And the volume of the universe, the size of the universe, is increasing with time based on this redshift, or decreasing with time based on this redshift. So when we see an image of the universe at redshift 7.5, what we're really seeing is a time when the universe was smaller by a factor of 1 plus 7.5 cubed because of the way the volume of the universe works. So we're actually seeing a snapshot when the universe was much smaller in time. But we can also then work out exactly what the distances are based on exactly that measurement. Okay,
well, the reason I'm asking you this, and this is something I struggle with almost every time I talk about this topic, and that is the size of the universe versus how far away things are and redshifts and stuff like that. You guys are all familiar with Ned Wright, right? He's a cosmologist. He's got a website that I use a lot on the he's got a cosmology calculator that I use quite a bit. And let me show you something that he says. Let me get my screen share going here real quick. And so here's something that he mentions, I don't know if you guys can see this very much, but it's like why light travel time should not be used in press releases. And he makes the point that these numbers Z that we're talking about is unambiguous, and it's the one that we want to talk about when we talk about very distant objects. But he also says that it avoids some of the appearance of speeds greater than the speed of light, or universes larger than the light travel time and things like that. Do you guys want to comment on what this means and kind of help us get our heads around this? Because when you say the universe we're looking at something in a certain z distance away, you can actually have a universe that's larger than the size of say than the age of the universe, right? 13.7 billion years. The size of the universe can be larger than that.
So I can give you one answer to this question based on the amount of feedback I got from the various articles that were written. So Ned's right. The thing we actually measure is this redshift. You know, we measured this Lyman alpha emission line, which is an emission line of hydrogen, which should be well in the UV, and we measure it in the infrared. And so the ratio of the wavelengths that we observe it at to where we know it should be is 8.51, which is equal to 1 plus the redshift, so the redshift is 7.51. So that's an unambiguous number. Okay, to go from that to any other property we've mentioned, you need a cosmological model, and that's where Ned Wright's great website comes in, or you can use a number of software packages. And for that, you need to know, okay, how fast is the universe expanding now, which we call the Hubble constant, how much matter is there in the universe, and how much dark energy is there in the universe. We do have pretty good ideas on those of what those parameters are, even better now with the recent results from Planck. So if you take those numbers, you can convert your redshift into a number of properties. The one that we tended to quote the most was the look-back time, which was 13.1 billion years. So we're seeing this galaxy as it was 13.1 billion years into the past, or the inverse of that, we're seeing it as it was 700 million years after the Big Bang, because the universe is about 13.8 billion years old. But that is not the actual distance to this galaxy. If you were to freeze the expansion of the universe, and I'll use something that Casey said that translates very well, and extend a tape measure out to this galaxy, and your tape measure was only 13.1 billion light years long, it would not get there. Because since that light has left this galaxy, since the photons we measured with Keck and Hubble left this galaxy, the universe has kept right on expanding. And so right now the galaxy is actually about 30 billion light years away from us. And that tends to confuse people because they say, wait, the universe is only 13.8 billion years old. How can something be 30 billion light years away from us? And that's because of this issue. The universe has kept expanding, and the space between galaxies has pushed our galaxies farther and farther apart, faster and faster and faster.
And what can limit that expansion rate? Does anybody know? What can limit is the expansion rate of space-time, for example, bound by any sort of limits, like a speed limit?
Make Dan do it. Make Dan do it.
Sure.
Dan, limit us.
Yeah, I mean, we thought that this expansion would be limited by gravity, by all the stuff in the universe attracting to each other and slowing that expansion down, and that's what they got the Nobel Prize for recently, was finding that the expansion is actually speeding up, and so that things are actually moving apart from each other faster and faster as time goes on more recently. And as far as we know, we think that's going to keep continuing indefinitely. But as far as we know, we think that the battle between gravity and acceleration, we think acceleration is winning.
And yeah, you were cutting out a little bit there, but I think we got most of what you were saying. So the expansion rate is also affected by lots of different things too, right? I mean, you've got these things. You've already Steve alluded to it already. There's things like dark energy, dark matter. These things also affect what the universe is doing as a whole too. So, was it always the same? Did the universe always expand at the same rate as, or did it speed up or slow down, or do we know yet?
Well, okay. I mean, I can chime in a little bit. You're actually going to push a little bit beyond my comfort zone, but I mean, in the past, we think the universe was expanding faster than it is today. So, when we're seeing the expansion of the universe at redshift 7.5, it's actually happening much faster. And over time, it was gradually slowing down simply because the amount of mass in the universe was acting like gravitational, it was acting to just hold the universe together and slow down that expansion. And it's only been recently that we've seen the evidence that dark energy has started recently to cause that expansion to speed up. It's only been in the last, really, for you astronomers, since redshift 0.4 that dark energy has even had the same effect as all the dark matter in the universe. But of course, as the universe gets bigger, the mass density is dropping, and the dark energy effect seems to be increasing. Now, just to come back to one thing, I mean, it was not always like this. In fact, we think there was an early period in the universe when something magical called inflation happened to create something macroscopic like the universe. And at that point, stuff I actually understand says the universe would have been expanding faster than the speed of light. And there's nothing wrong with that because you don't violate causality, but this actually goes a long way to explain some of the problems with the Big Bang if the universe went through this very early period where it was growing exponentially. And the space between, well, they weren't galaxies, but the space between everywhere was actually growing faster than the speed of light. So we know the universe has gone through these sort of weird phase changes before. And I think as Dan pointed out, we don't know what's going to happen in the future. We can only try to speculate based on what we see now.
Yeah, I'm glad you brought that up. So the inflationary period was this really amazing time where the universe went from being really small to being really big in a very short amount of time, and it grew exponentially. Has there ever been a period like that again? Has there only been one?
As far as we know, there's only been one, right? But we only live in one universe. We only have one data point where the universe would have gone through this exponential growth. It's funny though because I mean, dark energy is acting a little bit like whatever it was that caused that early inflationary period, where it actually caused this the expansion to accelerate out of control. Now, I mean, the early inflation, it would have happened. I mean, like you said, it's an infinitesimal amount of time. I mean, 10 to the minus 30 seconds or something like that. Whereas today, of course, we measure time on much longer time scales. So dark energy is much slower acting compared to that. But no, as far as we know, it only happened once.
So while we're on the topic here of the early universe, the very early one, let's talk about what came after that. So we have the Big Bang. We have this period where inflation pushed everything apart, or the universe expanded. We'll say pushed apart. That's misleading. The universe expanded to something very large in a very small amount of time, at an exponential rate. What came next?
Well, are you going to take it, Mark?
Oh, sure, I can take it. So you had a period in which the universe was relatively uniform. The material in the universe, the matter, and both the dark matter, the gas, the photons, everything was sort of very uniform. And wow, and
Casey's over there taking pictures.
and in particular, the gas in the universe, it was a very hot, dense, young universe. The gas in the universe was ionized, which means that most of the material, the normal, what we call baryonic matter in the universe, is hydrogen gas, and the protons and electrons were separate from one another because the temperature was so high. At some point, as the universe expands, it's cooling down. It's cooling down as it grows. And at some point, it gets cool enough that the electrons recombine with the protons to form hydrogen atoms. Now, that's just physics. I mean, that just happens when the gas cools enough. But it has particular consequences for what we're interested in. One is that photons, when the universe was ionized, photons of light scatter off those electrons very efficiently, and so the universe is basically opaque. The photons, are constantly scattering off those electrons. When the hydrogen atoms recombine, the photons are suddenly.
Okay, don't wait. Before you go too far, I got to explain that. Opaque is an interesting term, and it's one that I want to make sure people understand. Early in the period of time you're talking about, where there was all these ionized particles. That means there were nuclei and there were electrons floating around, but they weren't as atoms yet. A photon would travel and wouldn't go very far before it hit something and couldn't go. So that's what you mean by opaque. A photon simply couldn't go very far before hitting something else and reionizing something else, which is why the universe was the way it was. However, the universe was getting bigger. And as it got bigger, there was more space. Correct me if I'm wrong here, okay, if I say anything wrong. But there's more space, and that photon can travel a little bit further, and eventually it reaches a point where photons...
No, it's not really that. The important thing is that the universe is cooling down, okay?
But it's doing that also by getting larger, right?
It's cooling down because it's expanding. As the universe expands, it cools. It's like if you take a box of air and compress it, okay, that air heats up. If you expand it, that air cools down.
That's right. That's okay. That's what I was getting at when I said was the things were getting larger.
Right.
Okay.
So the universe expands, the gas cools, and at some point, if hydrogen gas is higher than a certain temperature, it will be ionized. The electrons are separate from the protons. When it cools down below a certain temperature, that happens at a certain redshift. We can map the temperature and the redshift to one another very exactly. And at a redshift of about 1,000, roughly, the universe, and that's, so who remembers, 300,000 years after the Big Bang?
Right. Yeah.
The universe cools down enough so that the hydrogen atoms become hydrogen atoms. I mean, the electrons and the protons go together, you get a hydrogen atom, and now at that point, those photons no longer scatter off the electrons. They can just travel. Okay?
And so boom, we have the electrons are free, they're going everywhere, and I'm sorry, they're free.
The electrons are trapped, and the photons are free.
And so now, and this is roughly around 300,000 years after the Big Bang, and was the period immortalized by the image we see with the cosmic microwave background, correct?
Exactly.
Right. In fact, that is the cosmic microwave background radiation.
Yes.
From this process.
So one of the first things we learned from that microwave background, that's our map of what the density or temperature distribution of the universe looked like at a very early time, long before there were galaxies. And those fluctuations, those little bright and dark spots that you see in the microwave background, those are all the seeds of higher and lower density regions that will eventually grow to become the galaxies that we're studying later and that we live in today.
Great, and that brings us now to this period, which I think Dan wanted to make a few comments on, which I think we should try. And this, so we've got this period where the galaxies are starting to be formed, and in a I may not have this right. There's a period where reionization happens. These atoms are being split apart again. They're starting not being split apart, but they're being stripped again to become ions. Is that correct, Dan?
Sure. So as the universe is cooled, the photons no longer have enough energy to strip the electrons off of the protons. So the electrons and the protons have all been able to get together now.
Right.
Photons are no longer energetic enough. But now once you get stars forming and galaxies forming, now you have things burning, you have photons that are now more energetic, and you have photons that are now able to reionize or to split apart these electrons from these protons again. And so the electrons are basically in the way again, or these atoms are now in the way of these photons that are trying to travel.
And
so
these are from the stellar winds of these brand new stars, essentially, right?
Well, they're from the stars themselves. So
and the starlight that comes from all these.
Right. So these energetic light, these photons, and so now there's stuff in the way, and this actually gets to Steve's discovery of this confirmation of this this most distant confirmation of a galaxy is really pushing the limits, and it's going to be interesting to see how much further we can push this, because now we're really he's really pushed back into this time where there were these electrons and protons together, and these photons were bumping into them and they weren't able to reach us. And so maybe you want to talk a little bit about that, because you had to observe some 42 galaxies in order to find this one with this emission that was able to reach us.
Yeah, that's right. So the key here is the tracer we're using for these galaxies. It's this thing we call the Lyman alpha emission line from hydrogen. And you get these photons when a hydrogen, the electron in the hydrogen is in the first excited state, and it goes down to the ground state and emits this photon. The problem with that photon is if on its way to Earth it comes anywhere near any other neutral hydrogen, it has that right energy to get reabsorbed and excite that hydrogen atom. Now, the hydrogen atom will really quickly re-emit that photon, get rid of it, but it will do it in a random direction. And this is a process called resonant scattering. And so if you have kind of a beam of these Lyman alpha photons coming towards Earth, but there's a bunch of neutral gas in the way, the neutral gas will scatter it and make it really diffuse and make it really hard to see. And luckily for all of us who have been trying to confirm the distances to galaxies for several years, at least as high as a redshift of 6, so about 1 billion years after the Big Bang, the space between galaxies is ionized. This is, reionization happened earlier than that. From now till then, it's ionized, so Lyman alpha photons can happily travel through the space between galaxies and get to our telescopes. But about, I guess now 3 years ago, there started to be hints that at redshift 6.5 or higher, there started to be some problems. At a redshift of 6 or so, it was really easy if you had a big enough telescope and looked long enough to see Lyman alpha from most galaxies you looked at. Anywhere from 50 to 80% of galaxies showed this emission line. But at redshift 6.5, for some reason, that fraction went down to about 10 to 20%. And that's essentially consistent with what we see now at redshift 7.5. We only saw 1 out of 40, but we didn't actually expect to see all 40 because some are too faint, and some may have been slightly out of the spectral range we used. But we did expect to see about 6, and so we expected 1 out of, and we only saw 1, so that's about 15%. And so there are a few effects which could do this, but the easiest one conclusion to jump to is, well, maybe the space between galaxies is starting to be neutral again, and that's clobbering these Lyman alpha photons and not allowing us to see them from most galaxies.
So in the galaxy you observed, you did or did not see the Lyman alpha emission?
We did, and so that's interesting. So if the space between galaxies has neutral gas, how the heck are we seeing this one?
That's good. Thank you. I thought I was going crazy here. I thought, why is he saying it's absorbed and then he sees it here? Okay, good.
Right. So we think, and again, we don't know, we think from theoretical models that reionization is essentially clumpy or inhomogeneous. The most overdense regions ionize first, and other regions aren't yet ionized. And so our galaxy, which is really bright, may just sit in an ionized bubble, which allows this photon to get out and be transmitted through to Earth.
Okay, so early galaxies are not going to ordinarily show us much in the Lyman alpha part of the spectrum, but you happen to find one that might have been in an area where that was possible.
That's right.
Okay, and so and that is, and one of the important indicators of this emission line is whether or not it helps us to see if there's much ionization in the area.
Sort of. It's a little bit more complicated than that because we know there's lots of gas within the galaxies, and so certainly gas in the galaxies can sort of block this line as well. And that's why, you know, at lower redshift, we don't see this from all galaxies, only from some. And so it could be that some property of the galaxies is changing. You know, Casey mentioned earlier that these galaxies have lots of gas. Maybe they have so much gas so close to the Big Bang that the line can't make it out. And so it's not 100% that we're seeing reionization, but we know it's got to be happening sometime, you know, around this redshift, and so it's probably having some effect. And so it kind of paints a dim picture for using Lyman alpha to measure the redshifts to galaxies at even higher redshift. Although the next generation of 6-meter space-based and 25 to 30-meter ground-based telescopes will have a much greater sensitivity, and so still should be able to make some progress.
Okay, so I just want to take a quick step back and talk a little bit about what, we used a lot of terminology there, Lyman alpha emission, things like that. What he's talking about is simply looking at a spectrum of a galaxy, and at certain parts of that spectrum, you'll see bright lines appearing. And where those lines are in the spectrum will tell you all kinds of different properties of that galaxy. And the one he's talking about is one specific one in the Lyman alpha portion. What wavelength is that, roughly?
So we were looking at it, we observed it at about 1 micron, which is a little bit redder than the eye can see.
So that's 1 micron, which is pretty heavy. Yes, like you said, it's right. It's in the near IR, and so.
But just to be clear, I mean, it's actually something that's emitted at 0.1 microns, 0.12 at 1,200 angstroms at the ultraviolet, and the universe has expanded so much.
Thank you.
Let's light out all the way from the ultraviolet out to the infrared.
Thank you. Okay, thank you. Yes, of course. Thanks for that clarification.
Can I try and show the spectrum? Will that help? I don't know if I click the screen share button. Will that show?
Pictures are worth 1,000 words. Absolutely.
All right, let's take a look.
Spectrum is worth 1,000 pictures.
There we go.
Spoken like a real spectroscopist.
All right, just a minute.
Somebody
now I
had to do
it.
Okay, so what are we looking at, Steve? You got to explain.
Is it showing it yet?
Yep, we can see it.
Oh, cool. Okay, there we go. All right. So this is our spectrum. This is what happens when you take a 10-meter telescope, the biggest we have in the world, and stare at one galaxy for 6 hours. You get this little blip. And so in the top panel that almost looks like a little image, you see this kind of white fuzzy thing towards the middle. That's the Lyman alpha line. That's it. And the bottom, we're kind of looking at a one-dimensional cross-cut around that. So you see nothing except for right where this line is, we see a bump. And so we already had a pretty good idea of what the distance was for this galaxy, so we don't think this line could be anything else. We could talk about that for another hour if we want to, and we surely spent many pages in the paper talking about that, but we're pretty sure it's Lyman alpha. And so then we just simply look, okay, what wavelength do we see it at? we see it at 1.034 microns, and actually those numbers along the top, those are the redshift, and that tells us that's at redshift 7.51.
Beautiful.
And so if it was at a little bit lower redshift, we would see a similar blip. It would just be a little bit to the left on this plot.
And this came from what instrument?
This is from an awesome new instrument called MOSFIRE on Keck. It's extremely sensitive. That's one of the, one of the reasons why this was doable now is with this brand new instrument. It's very sensitive, and it can look at 40 galaxies at a time. Whereas before a year ago, you were restricted to, for the most part, only looking at one galaxy at a time with spectrographs that were not as sensitive.
And there's your confirmation, folks, right there. So Dan, when are we going to see one of those of your galaxy?
Right. So I said that we're following my galaxy up with the Hubble telescope, and I said we'll obtain a spectrum of it and try to confirm the distance. It's actually a lot more difficult than that, and I don't actually expect to see that blip in the image in the spectrum. And so like Steve was saying, I mean, it gets harder and harder the further you go back in distance. More and more of the universe is probably in this neutral fog where the photons can't escape. So looking at just one galaxy like that, the odds of seeing it aren't that good. So what I'm going to get is a spectrum where you basically see I'm hoping to see light emitted on one side of the spectrum and no light emitted on the other side. And so that's the other feature that about this Lyman alpha wavelength is that you see emission at the wavelength, and everything blueward of that is energetic enough to ionize these photons and get absorbed and then re-emitted, like Steve was saying. Anything that's redder is not energetic enough to knock an electron off of an atom, a hydrogen atom basically, and so it streams free. So we see all of the light that's redder than that wavelength, and we don't see the light that's bluer, and that's what I'm hoping to see in this Hubble spectrum that I'm obtaining.
How would that confirm your distance, though? Right.
So it doesn't have the same. You won't see that line at that exact point, and that kind of confirmation is probably going to have to wait for the James Webb Space Telescope.
Oh, good.
It's going to help.
Okay.
So.
Nice. Okay. Well,
it's pretty good though. I mean, I would say for those of us who have spent a lot of time looking at spectra of distant galaxies, if we see a sharp break and it's big enough, like what Dan describes in the spectrum, I would count that as pretty solid. I mean, in fact, that's really what Dan described. The fact that the light shortward of a certain wavelength gets absorbed and disappears completely. That's how we pick these galaxies to begin with. That's where this Lyman break technique comes in, which is a color selection technique based on where this Lyman alpha break occurs. That's how we pick these galaxies to begin with. It's one of the reasons why we believed that Steve's galaxy was at redshift 7.5, why the evidence is very good for Dan's galaxy being at redshift of 11. But with filters, you can't pin that break down exactly. If you see a sharp break in a spectrum like that and the quality of the data is good enough, I think that'll be quite convincing.
Okay, so when are these Hubble observations going to happen, Dan?
In May and December of 2014.
Okay, good. I see. I predict another hangout in our future.
So we're safe until then, is what you're telling me.
Right. So Steve, you've got the first confirmed record until then. So,
we have. So Clash has other galaxies we've observed, and so this is these are the two different programs we've been observing with. So Steve and his group, they're working on the Candle survey with Hubble. Our group is working on the Clash. These are two of the largest surveys ever undertaken with the Hubble telescope. And they basically highlight two ways of finding these distant galaxies. With Candles, they observed a large portion of the sky. And with Clash, we observed these lensing clusters, which we've talked about on previous Hangouts. They magnify distant galaxies, help bring them into view. And both of our surveys just completed observations, I guess, a few months ago now. And so we're still going through what we found and following up these observations. And so, as a matter of fact, Rensky and Larry Bradley were just out at Subaru, I think, and they were taking spectra of more of these galaxies. Yeah, if you want to say a little more about that. And we have other ones that we're still proposing for. And So we might try to go after your record still, but
Okay. So Renske, you were at a Subaru trying to confirm some of these.
Yeah, well, we use Subaru because we have galaxies that are just slightly under redshift 7, so we could use a more conventional spectrograph. Unfortunately, we had a bit of bad weather actually most of the week. But
the problems of ground-based observatories.
I wish everything could be Hubble. Just
Maybe Steve was doing his rain dance.
Well, actually, we had another night on Mossfire 1 week ago. Maybe it was even the same night because we couldn't even open the dome. It was icy. So we were hoping to break our own record. Not only we were looking at one of the other Candles fields, we also started looking at the Frontier fields. The Frontier field program just started the cluster Abell 2744, and so we spent a frantic 36 hours getting the data, looking at the data, trying to find, and we found a few pretty good, bright, high redshift galaxies that I'm sure Dan and maybe some other people are already looking at as well. And we were hoping to have the luck of the calendar, observe them right away, and weather happened, and it didn't happen. So you might have to wait till next year.
Okay, before I get to some of the questions, guys, I want to. This particular panel sort of inspired me to want to ask this because one of the questions that I get a lot in the course of doing all of these hangouts and making videos on YouTube and doing all kinds of things like that is I'd like to talk a little bit about what it's like to do your job. And since we have a PhD student here as well as some senior people, I'd like to ask, first of all, Renske, let me ask you this question: what made you go into astronomy in the first place? What inspired you to get started in this career?
To study it as undergrad?
Yes, yeah, to study it. What made you want to become a student or PhD student in astronomy?
Well, I didn't even know you could be an astronomer, but I really liked physics in high school always. So I just I started out just wanting to do physics, and then I sort of discovered that you could be an astronomer, and I think it just doing the classes, and it's so incredibly interesting to learn about this whole world that I didn't even know existed.
So you didn't go out thinking that you'd want to start doing this?
No, I mean it's such a small field. Not everybody knows you can be an astronomer, or it's not everybody follows Hubble Hangouts and knows about these things. So I didn't, and but yeah, I discovered it along the way.
And what were some of the things? Can you tell us some of the biggest challenges you faced while you were in school? What advice would you give to somebody who's just thinking about this as a career? And what advice would you give them based on what you've learned?
Well, I think what I mostly learned is that not just astronomy, but also physics, there's so much more to learn than you learn in high school. I always thought in high school physics is okay, but when you get to universities, when you learn the really interesting stuff, the quantum mechanics, the relativity, all of that is just so much more interesting than you think it is. Or me, I always, my view of physics was okay, but I never really loved it until I went into depth and really studied the most difficult problems. And that is just so exciting that it's so difficult, and you learn things that you didn't know that were out there. So,
okay. Great. Well, how long do you have? When will you be getting your doctorate?
Next year.
Awesome. All right. Well, good luck and congratulations. And it's really great to meet you. And I'm glad you were here to help us out with this hangout. So the guys that work at universities, let's see, that would be Steve and I believe Casey. What do you guys have any advice for like prospective students, people who are thinking about being an astronomer but aren't sure if it's for them? Who wants to go?
Go ahead, Casey.
Well, I guess I can start a little bit. I mean, it's something. I think if you're going to go into graduate school for it, it's something you've just had a passion for. Maybe like Renske say, which is I think we probably all experienced this, where astronomy's just been something we've loved to do forever, and you have to have that real passion for it. I mean, it's something you just want to do a lot of and learn everything you possibly can about. For me, I mean, astronomy is, I think like Renske, I always liked physics, and then you kind of learn that physics on Earth is sort of just the tip of the iceberg, and once you get out into the universe, that's where you really hit the extremes, and there's just so much to wonder and imagine out there. There's always the thrill of discovery, that you're seeing something for the first time that no one has ever seen before, and you never really lose that. And so if you're one of those people who really feels that kind of drive, then, you know, pursuing astronomy or astrophysics is the way to go. Partly, I also say you have to have that love for it, because at some point during your graduate student training, it's going to just become so tedious and so exhausting that if you don't go in with that love for it, those two aren't really going to cancel out, and it might be more frustrating than you think. I'm going to say everybody on this call, we probably all have that passion for it, at least at some point in our lives, unless it's already been crushed from us.
Okay, Steve, you got anything to say? Any comments?
Yeah, and in Casey's right, you know, you will be tested not just at one point, but at multiple points throughout your career. So you do need to have a passion. You know, an important thing, I think a lot of people get interested in astronomy. You know, I'm teaching undergrads now, and they say it's very interesting. Oh, but I could never do that. And I don't think that's true. You don't have to be a genius. You know, not everybody is Einstein. You have to have a passion, you have to like science, and you have to like math, which I know a lot of people don't, but you know, practice and get good at it, and you just have to be a hard worker. And you know, maybe with a splash of creativity thrown in, but you far and away do not have to be a genius. You just have to really like it and really be willing to work hard to do what you want to do, to spend your days looking at stars.
And I can
Galaxies.
definitely
sorry, not stars, galaxies.
Actually,
right. And using spectroscopes and not or spectrographs and not images, right, Mark? So so I just want to back up what Steve said, just because I want to tell you. I mean, I didn't go to graduate school. I don't have a doctorate, but I did have a hard time with math. I do have a bachelor's degree in physics, and getting that degree was something I'd always had a dream for, but I worried for a really long time whether I was going to have the actual ability to do the work. And it was simply by doing what Steve said. I just kept at it. For me, the answer was computer programming. By becoming a software engineer, it wired my brain in a way that allowed me to do the advanced math I needed to do, but that's a whole story in itself. But over doing that over years and years, I was able to finally realize, wait a minute, I can do the math now. And that's what enabled me to go ahead and go forth and get my degree. So it isn't always a matter of just having this innate brilliance. If you in fact, it can get in the way a lot of times. If you can work very hard, like Steve said, it really does make a difference. So let me get to some of the questions real quick. I hear this one is from YouTube. I'm sorry, from the event list. And it's Domin Kastner, who says, this question is more fit to the end of the show. Well, we're there. What do you expect in the next 10 years in optics technology, and how far will we be able to see then? Anybody? Next 10 years of optics technology.
Well, we can certainly talk about the James Webb Space Telescope.
I was hoping somebody, yes, we certainly can.
it has a number of advantages. Dan, as the representative of Space Telescope, I don't know if you want to take this one.
Well, right, it'll observe further into the infrared, like we've talked about, so light that's more and more stretched out earlier, from earlier in the universe, and it's a larger mirror, so it'll be able to collect more light and see fainter things, and hopefully see the first galaxies with some caveats, as Steve mentioned. But there are other telescopes that are planned and being built.
And so so James Webb is hopefully going to show us some of the first galaxies ever, and with some of the earliest stars we've ever seen. And so I was talking to Massimo Stiavelli, the project manager, and he was telling me the very first stars are going to be something that James Webb will be able to show. So that goes back pretty far. Also, from Claudette Johnson is asking, and maybe this was a good one for you, Dan, how long will the Hubble continue its mission?
We're hoping it'll overlap with the James Webb Space Telescope, so for a year of overlap with that. And then at some point we won't be able to operate both of them at the same time. But there aren't any more servicing missions planned, so we just hope it keeps going. And it's performing better than ever. I mean, it has all new instruments from the most recent servicing mission, and so it's in top form right now. And so there's plenty more it can do. We mentioned the frontier fields it's doing right now. There's plenty of more big science that it can do, and we're looking forward to.
Yeah. An interesting point with that is people might think that after 23 years or so, we may have run out of ideas for Hubble, but we write proposals annually to get new observations, and the success rate of these proposals is usually between 10 and 15%. So there's something like 7 to 10 times more ideas than we actually have time to execute.
We really need something like 10 Hubbles, and
and then we'd all get our data.
Right.
Okay, folks. Well, unfortunately, Steve has to go because he's got to get out of here and go to another thing. But I want to thank all of you guys for showing up, and thank you also for your patience in my not being able to get the get some of these graphics up right away. I usually have a lot of help with other people, and I was wrangling astronomers. Oh, I have one quick question. What's the difference? What do you guys consider yourselves, astronomers or cosmologists, or neither? And what's the difference?
It depends if you want to talk to the person next to you on the airplane or not. So if you're
so which one's sexier?
Well, you can say you're an astrophysicist, and that usually intimidates people too much. But I usually say I'm an astronomer.
Do you say astronomer? Do any of you consider yourselves cosmologists?
Not. I mean, I think probably in one way or another, many of us have been involved in projects that are more cosmology oriented. Cosmology. When I think of a cosmologist, I think of someone who really studies, fundamental things about the structure or expansion of the universe. And we talked about that, right? I mean, I don't think any of us made complete fools of ourselves talking about cosmology during the course of this hangout when we talked about inflation and recombination and reionization. Those are kind of the rate of expansion of the universe and dark energy. That's kind of cosmology stuff. For me, astronomer speaks more to the person who goes out and observes galaxies with telescopes. Now, sometimes you do cosmology by observing those galaxies. Sometimes you're doing astronomy and trying to understand the galaxies, the stars, and then how they formed and that kind of thing. So I feel like I'm more of an astronomer, but I've certainly been involved, for example, with some of these projects that have studied the acceleration of the universe, which is more of a cosmology thing.
Yeah, and it's also less likely to confuse somebody with cosmetology, I guess, as well. So, anyway, I was just curious about that because I noticed some people refer to themselves as cosmologists, other people astrophysicists and astronomers, and I think Dan's right. Dan's hit on something there. It's pretty impressive to say astrophysicist, not so much maybe cosmologist. I don't know, but anyway, I was just curious about what you guys considered yourselves, and I want to thank you guys all for coming. That's it for this time around, Hubble Huggers. I really appreciate your watching, and the next one will be scheduled after Thanksgiving, but I want to do a quick plug that NASA Goddard is doing a hangout on Thanksgiving Day. I will be, if you follow any of my Twitter, social media stuff, I will make sure that you get the link where they're going to be looking at Comet Ison as it goes around the sun through the eyes of the Solar Dynamics Observatory live. So please tune in for that. It's on Thanksgiving Day, and I'll send out more information as soon as I get that. My next hangout will probably be, I'm hoping, with Dr. Sarah Seeger. We're going to talk about exoplanets and some of the Kepler results. That will be the week after Thanksgiving, and I will, as soon as I get a date from her, I'll post the event. So that's what's coming up next. I hope you guys have a great weekend, and I want to thank all of you once again. Thank you guys very much. This has been a lot of fun.
Yeah,
Thanks, Tony.
All right. Talk to you guys soon, I hope. That's it for this time, Hubble Huggers. And as always, keep looking up.
Well, I think we'll talk a lot during this telecon about how we find these distant galaxies.
Yes.
But I'll skim over it for right now. So we use the Hubble Space Telescope, and we take lots of really great, really long duration images of the universe to try and find really distant galaxies. And you can do this in a variety of ways, but we basically rely on the colors of the galaxies to figure out which ones we think are far away. And broadly speaking, we look for the really red things. We know that because the universe is expanding, things that are really far away from us are moving really fast away from us. And due to the Doppler effect, or the stretching of light waves from really quickly moving objects, they tend to look really red. And so we can get a pretty good estimate of which ones are far away by essentially looking for the red things. But to be certain about their distance, we need to follow it up with spectroscopy from the ground and try and measure a very precise distance to those galaxies, not only to get a precise distance instead of just an estimate, but also to make sure we're not kind of folding in some lower redshift or more close to home galaxies that can masquerade as these distant galaxies. For example, there are low redshift galaxies that are just red because they're old or have lots of dust, and so we need to make sure they're not in our sample.
So you're looking at various areas with the Hubble, and then you see them in red filters, or you see them with certain optical properties, and then you want to go back and look at them again with ground-based telescopes or some other telescope to confirm that they are in fact not just inherently red.
Yeah.
So the nature the Nature headline reads, "A galaxy rapidly forming star 700 million years ago after the Big Bang at redshift 7.51." So, is this the most distant galaxy? As part of a survey, the CLASH survey, if I recall, and using gravitational lensing. And but you're saying that that while you're confident of the number, it has not been spectroscopically confirmed yet, correct?
That's right.
Okay, and Stephen, yours has. So right now, the important thing is, it's kind of like Kepler with exoplanets. Kepler comes up with a lot of candidate exoplanets, but it's not until someone else goes behind and actually confirms that they're there through some other means, whether more light curves or more accurate measurements, can we be sure that those things are really there. So that's pretty important. So Renska, can you tell us a little bit about what was your role here? What were you a part of this team?
No, I'm part of the CLASH team, but I wasn't part of either of those candidates.
So are these things then that you're studying as part of your PhD work?
I am studying a couple of galaxies at redshift 7, but they're not quite the highest redshift galaxy. We're not trying to find the highest. We're not trying to go for that record. What I think is really interesting about Stephen's object is the fact that it also in the Spitzer colors there's very peculiar colors, which might be due to oxygen. And well, we don't know what it means yet, but I'm also looking at objects that have very interesting Spitzer colors. And might be oxygen rich or ionized oxygen rich. Yeah.
Okay, great. And so, what is it when you say we've seen so far?
That's the question of the hour, I think. So, when we find galaxies with images, we frequently refer to them as candidates for galaxies because we are not absolutely sure of their distance until we follow them up and detect them with spectroscopy. It's extremely difficult because they're really far away, so most of these most distant galaxies we hear about remain candidates for now. Most of them, and as Dan will tell us a little bit, we think are probably real, but we don't know. And so we refer to this one as the most distant spectroscopically confirmed galaxy that we know of. And so many of the other ones may be likely real, including Dan's that he's published as well, but we don't know until we get a spectrum.
So this one's confirmed then. It really is a 7.51.
That's right.
All right, well, Dan, a while back, you and I had a little hangout, I recall, and you were telling us of a galaxy how far away? What was the redshift on that?
So it's redshift 11.
Okay.
And so that's 420 million years after the Big Bang. And I guess Steve's is, what's the number on your, Steve?
7.51.
Yeah,
Right.
700 million years after the Big Bang.
Right.
Measly 280 million year difference.
Right.
Right.
Not the rubber. But as Steve said, I mean, this spectroscopic redshift really is the gold standard for these distant measurements, and it's a confirmation of how far away it is. And we're also pretty confident in ours being at its distance, but we actually have observations coming up on the Hubble telescope to try to get a spectrum of this galaxy and to try to confirm this the distance for that one too.
Okay, so the Z11 galaxy that you were talking about earlier was found in distant galaxies as well, because you may remember, if you've been following these Hubble Hangouts for any length of time, he had one or two things to say about faraway galaxies, and we're going to talk to him a little bit more as well. Also, who just joined us, Casey, and I'm going to have you pronounce your last name for me.
Sure, Casey Papovich.
Casey Papovich, and you don't have your lower third up. You just joined us, so can you tell us where you're from also?
Sure, I'm at Texas A&M here in College Station, Texas.
Oh, welcome. Okay, great. And I didn't get a chance to brief you on what to expect. You're going in cold turkey. We're live right now, so if you have any questions or if you have any problems with anything, let me know, and we'll all sort of step you through it. So anyway, welcome everybody. You may notice that we don't have Alberto here today. He has not joined us because he is still getting set up in his new job over at Northrop Grumman, so he will hopefully be joining us in the next hangout that we're going to be having after Thanksgiving. And Scott Lewis also couldn't make it. So it's me here moderating the whole thing. I hope you, I'll ask for your patience if it takes me a while to get certain things up on the screen share. So let's get started. The reason we're having this hangout is there was an announcement a while back about a new, and let me just read the press release headline because to me it was a little bit, you see these all the time. Astronomer, comma, with international team, comma, identifies earliest galaxy ever detected. And we seem to be seeing a lot of these kinds of headlines. And so, Stephen, you were the lead author on a paper, I believe, with, I believe it was in Nature, correct?
Yeah, that's right.
Okay, you want to tell us a little bit about it?
Sure. So,
Tough ones.
Okay, hello everybody, and welcome to the latest Hubble Hangout. Today, my name is Tony Darnell. I'm the social media manager at the Space Telescope Science Institute, and today we're going to be talking about very, very far away things, notably the most distant galaxies we've ever seen. And with me today, I've got lots of really I'm assuming highly qualified people to be able to talk about this. No, I'm just kidding. We have a lot of experts, and so we talk about some new discoveries on some of the most distant galaxies we've seen so far. With me, but before I get started, let me just say we are ready to take your questions and comments. Casey just joined us. Via Twitter with the hashtag Hubble Hangouts. If you can comment on our event page as well as on the YouTube channel. I'm looking at comments on there as well as you can ask us directly here in the Google Plus event page. Already we're starting to get some questions now, so that's great. So with me today is Dr. Stephen Finkelstein from the University of Texas at Austin. Hi, Steve. How you doing?
Good. Hi, Tony.
Good, thank you. And with me is also Renska Smit from Leiden University. Hi, Renska.
Hey, how are you?
Hi, I'm good, thank you. Also back from the Frontier Fields Hangout, we might remember Mark Dickinson from the NOAO. Hi, Mark.
Hi there.
And a good friend of mine, Dan Coe, at the he's a you are a postdoc, right? At Space Telescope Science.
I'm on the staff now, actually.
Oh, are you? Congratulations. Okay, and he's the
you can buy us a drink next time.
That's right. That's right. Congratulations, Dan. He's with also with Space Telescope Science Institute, and he knows a thing or two about most